right. Good afternoon, everybody. My name is Ali Kujuri, and I am an adjunct professor at the Department of Engineering Science and one of the organizers of this lecture series. On behalf of the department and the School of Science and Technology, let me welcome you all to this 10th lecture of the academic year and 97th lecture in this lecture series since the start in 2006. And my thanks also go to Advent Technologies for sponsoring this lecture series since the start, as I mentioned, in 2006. Let me just make a couple of short announcements, and then I want to give the floor to my colleague, Dr. Strike, to introduce her, and I'll tell you why. First, we have ordered pizza, which is going to arrive at 5:30, right after the lecture. And then the next lecture will be on April the 2nd, 2015. The title of the talk will be The Electrical Grid of the Future, featuring a smart grid, distributed resources, and energy storage. It's going to be given by Mr. Jim Iyer, Senior Analyst and Principal E&I Consulting and Senior Advisor to the California Energy Storage Alliance. So let me introduce Dr. Strike, and he's going to tell you about all of the goodies.
I got it.
No, there is,
Oh, this is the one I'm supposed to use.
No, you can use it.
Okay, well, it's great. It's a great pleasure to introduce Heidi Barnes. I met Heidi a few years ago. I actually hired her. I guess it was Hewlett-Packard at the time.
I did come back at Hewlett-Packard time.
Hewlett-Packard, and then it turned to Agilent, and then now it's Keysight Technologies. I have trouble keeping up with the names of that company. But anyway, Heidi she grew up in Sebastopol, where I happen to live. She went to Caltech. By the way, I heard an interesting story about your application to Stanford, writing the essay in crayon. Anyway, Caltech, and then she went to NASA Stennis Space Center and did work on thin film solar cell design with ARCO also. At NASA Stennis, I guess you did work on hydrogen fire and gas detection for rocket engine testing, which would have been a really interesting project, especially for somebody like me that's a pyromaniac. She worked for me in RF design, RF circuit design, doing some RF modules that went into products that Hewlett-Packard and Agilent shipped. She then got involved with Verigy, which was a company that did test equipment for modules and for semiconductor wafers and various assorted things. Multi-probe tests, which is a very challenging area. While she was doing that, she learned a great deal about how you handle very high-speed signals on PC boards and other structures. That's a real challenge. There's a lot of engineering behind that. So today I'm very happy to introduce Heidi Barnes, who is our speaker for today. And by the way, the title of the talk is What is Signal and Power Integrity in Digital Systems and How It is Changing Our World?
Thank you very much, Don. Well, thank you for coming today. We'll get the slide up here. As we already mentioned, we keep changing our name. At Keysight, where I work, the new name, Keysight Technologies, a lot of us who have been there since the good old HP days, from a long time ago, we like to think of ourselves as Bill and Dave's company. Bill Hewlett and Dave Packard, and they started the company originally. And there's a very famous, I don't know if you read up on the history of Silicon Valley, there's a famous phrase called the HP way of how to do management. It's a very famous management style. And a lot of it boils down to just management by walking around. Managers that walk around and talk to the engineers and talk to the people and see what's going on. and having an open door policy where people can come in and talk to them at any time. And kind of an interesting bit of trivia, Steve Jobs from Apple actually had some of his first jobs at Hewlett-Packard and supposedly took that HP way to Apple when he started the company, along with, Steve Wozniak. But, basically, Bill and Dave's company is famous for test and measurement equipment. I believe you've heard a lot of speakers from Keysight. I'm not going to go into a lot of our products. In particular, though, I am actually working in our engineering design automation tools, or simulation tools, and most of them focus on high-frequency design because that's one of our strengths, especially here in Santa Rosa, is we do a lot of very high-frequency, high-speed electronics. So that's it for where I work. And the next slide, Dawn went through the list, and this kind of ties into, it's Women's History Month in engineering, and I kind of sat back and it's like, what does an engineer do? And if you think about it, or maybe you overthink it, it's not really easy to figure out how you get, how you end up where you are in the world. But if I look back, the way I kind of see things is I like to put physics to work to build things. I love building things. I love trying to figure out how things work. And so I think my suggestion as engineers is to never stop learning. Take advantage of whatever's put in front of you and apply your engineering skills. And as Dawn kind of mentioned, I thanks to Hewlett-Packard, I had a summer intern here in Santa Rosa when I was about 17 years old. And that started my engineering career. And I loved all of the different things they did in Santa Rosa. I worked in a plating shop. I worked in IC fabrication, worked on some instrument building. And that just got me excited about things. Went off into solar cells, went on to hydrogen fire and gas detection, rocket engine testing, came back to Hewlett-Packard, kind of got homesick, started raising my family. And I think the interesting thing is in yellow here, you can see I started at HP, it turned into Agilent, and I actually I got spun off, a typical thing in the engineering world, companies split, and maybe you get transferred. But it seemed to keep coming back to where I started, and there's a lot of great memories there, and I'm happy to be back at Keysight in their simulation tools department. So, let's go ahead and talk about signal and power integrity in digital systems and how it is changing our world. And let me see, my little animation is working. Does anybody know what that flashing light is doing? How many ham radio operators? Anybody a ham radio operator? SOS, right? Morse code, great. So I would say that's probably going at about maybe what I was guessing at 2 bits per second. So each one of those flashing of lights is a bit, and we can say, well, maybe we're getting about 2 bits per second. If you look over here on the right, we have a cloud server farm out there in some remote part of the world. And it's filled with little guys sending bits of information like this flashing light. And what's hard to really conceive or understand is that the server farm here, one little transmitter or sender is actually sending 25 billion bits per second. So think of that light flashing 25 billion times. And not only being able to flash that many times, but somebody else being able to listen and hear that and recover that information. I don't know how many SOSs that is, but quite a lot. So what are we talking about today? It's basically we have a talker, and we're talking about communication and what that takes. So we have to have a talker, and there has to be a listener. And in the world of signal integrity and communications and electronics, we typically call that a transmitter, is our talker, and the listener is our receiver, and there's some sort of connection here in between. There are billions of transmitters and receivers in the world. Just think about it. Everything from your cell phone, your computer, they all have to send and receive information, and a lot. And then if you look at the cloud that just keeps expanding in terms of just thousands and millions of these transmitters and receivers constantly sending data back and forth. So what is signal integrity? Why do we need a new specialty in engineering? What's so important here that it needs a new name? Well, just think about it. Here's this talker, and she's, I'm yelling as loud as I can. And you've got a listener. What? Eh? Can't hear you. And what we call this in the middle is the physical layer. And if it breaks, this phi is a sort of buzzword, they sometimes call it the physical layer. If it breaks, there's no communication. So it's actually a very important part of engineering, and they've called it signal integrity, where a signal integrity engineer makes sure that the physical layer can carry the data or information from the transmitter to the receiver. So that's the simple way of saying what a signal integrity engineer does. And basically they're an electrical engineer, but there's a lot of companies out there right now that are willing to pay extra for an engineer who really knows how to get the communications from the transmitter to the receiver. And like the slide says here, why can't I just be an electrical engineer? What's so special about signal integrity? Is it really that hard to get a signal from a transmitter to a receiver? They had those good old, back in the telegraph days, you just string a cable from the transmitter to the receiver, and this wire would string along for miles across the transcontinental telegraph, etc., to take these bits of information. Well, let's look back in history. And we would actually kind of say, where was the signal integrity engineer in 1858 when they laid the first transatlantic cable through the ocean? It turns out when they put that cable down, it started to work, but then it was starting to have some troubles, and I don't think they were an engineer. Maybe they're actually, I think maybe they were an engineer, but not a signal integrity engineer, because I believe the physicist came along and helped solve the problem. But there was a Mr. Whitehouse who decided the problem was it didn't have enough power. So he started turning the voltage up. He started increasing the power. He started yelling louder down the cable because he said that's going to fix the problem. Ended up burning up the cable. Not an easy thing to fix when it's under the Atlantic Ocean. So it took them probably another 10 or 15, or was it another 10 years or so to actually get it replaced. But back then they did not have signal integrity engineers. So let's take a little bit, before we get started jumping into a little bit more of the details of signal integrity engineer, they're in every industry, and you'll find that within whatever specialty you go into, there's usually someone who's kind of famous, who's written a book on that topic. And here we have Dr. Eric Bogatin. He's a graduate from MIT, and he calls himself the signal integrity evangelist. He goes around sort of preaching and teaching people all about signal integrity. And he has a book called Signal and Power Integrity that goes into what this area of engineering is all about. And so if you're interested and you find this topic exciting, it's a great book. He presents things from a physics point of view, and it's a very elegant approach to studying this topic. But the one thing that I'd like to bring out, and it's a good practice for all types of engineering, is never do a measurement or simulation without first anticipating what you expect to see. So before you build something and measure it, or before you design something and simulate it, have an idea, understand the physics of what you expect. So that's what we're going to be doing a lot today, is getting a better understanding of the physics, not really trying to understand the formulas and memorize them as much as getting some good analogies and concepts. And this one, what you realize is, why is signal integrity so hard? Well, what it turns out is it's kind of a simple thought, and if you look at what the physics is really doing and start analyzing, it basically comes down to a really simple thing. Time travel is not allowed. To get information from the transmitter to the receiver, it takes time, okay? There's a physical distance there. And so if I send a bit of information, if I look at an actual, if I have a level of voltage, say 0 volts, and then I have to transition to a 1 bit, or let's just say 1 volt. So I'm doing this transition. This is 1 bit of information to another bit. This transition doesn't happen instantaneously. In the real world, it actually has to ramp up. It takes time. And so I'm going to do a little simulation here. We actually have a length to our channel. We have a transmitter and receiver. And what we're going to look at is what happens if this rising edge to go from the 0 bit to a 1 bit is really slow versus what happens when it gets fast. And if you look at this transmitter, if I start my transition to a 1 bit, and if I'm transitioning very slowly, this is the blue line here. It's a very slow transition. It's coming along here, and it's slowly coming up to the 1 bit. Then one thing I notice is that the voltage level at the transmitter is almost the same voltage level at the receiver. Or another way of saying that is the bit that I'm transmitting, that same bit is at the transmitter as well as at the receiver. If the edge gets faster, suddenly now the voltage at the transmitter is a lot different than the receiver. And if the edge gets faster and faster, pretty soon I can have multiple bits in this channel at the same time. And so the bit of information that's at the transmitter is not the same bit that's at the receiver. I'm going to run the animation here, and you can kind of see how these... I'm going to have to... I forgot about that. And so you can see for a very slow rising edge, the voltage at the transmitter and the receiver are basically the same level. And then you'll see this will go much faster as our rising edge gets quicker. But the concept that you really want to grasp here is that the channel has a finite length, and these rising edges, as they get faster and faster, you can get multiple bits in the channel, that the voltage at the transmitter is not the same as the receiver. I'm going to kind of say this in a little bit simpler fashion, okay? How many people know what voice over IP is when you talk on the phone? There's a really frustrating thing that happens that's, I think people notice on voice over IP. When I'm talking, okay, my voice is traveling down that channel and I'm saying all these words, okay? I'm hearing these words I'm saying. The person at the other end is hearing completely different. They're not hearing the same words because there's time. It takes time for my voice to get to the listener. So the sounds and the words that are coming out of my voice or out of in front of me are not what the listener's hearing at the same time. There's a delay, and that delay can cause a lot of communication problems. And so really, that's what I was trying to express here, as that length gets very long compared to how fast I'm saying the words. There's a whole bunch of words in the channel, and the ones I'm saying are not the same ones that the person is hearing when you look at the same time. And so that can start to cause these problems of talking on top of each other and communications issues. And that's kind of the same thing that happens here, is that the transmitter's doing things, sending all these bits of information, but the receiver, if there's something wrong at the receiver end, it doesn't have time to tell it, hey, stop, slow down, you've got too much voltage, too little voltage, and so then you start running into some communication problems. So it's very important to understand how fast that rising edge is compared to the length of the channel. So if that rising edge is much faster than the length of the channel here, then you have the potential for communication problems. We talk about how fast the data goes in terms of how many bits of data can be transmitted in 1 second. And then the speed of the channel, there's some basic physics equations in terms of basically the speed of light, and then you divide by the dielectric constant of of the material you're in. And so there's just some basic physics for calculating how fast it's actually traveling in that material. So what happens when a signal travels through the channel? So along with the problem of having a lot of different bits of information in the channel at the same time, there's another problem, is that there's loss. And actually the dielectric loss is how your microwave works. Okay? The microwave has a frequency that's oscillating at, and the little magnetic dipoles in the material start to resonate. Most of the time it's water, and they start to vibrate. And the energy it's absorbing creates heat. Well, the same thing happens when you try to send a signal, a high-speed signal. These ones and zeros are changing real fast. There's a frequency content. And it excites that dielectric material, and some of that energy is lost. The other one I think most people are more familiar with is just the resistance of the metal. There is actually a little bit of what we call a resistive thermal loss, just because of the conductivity of that material. So these are things that happen as those bits of information are going through that channel. And one of the things we do with simulation tools that's actually pretty exciting is that I can take and graph the strength of my signal. I can look at the strength of the signal that's coming out over the strength of the signal that I put in. So it's just a ratio. And I usually do it in decibels, just because I'm looking over a wide dynamic range. But what I'm basically showing with this graph is how much, if my signal doesn't lose anything, then there's zero loss. And I have the ratio of the output to the input is 0 dB. But if I have any loss, you'll see the signal starts getting smaller in strength here. And what I'm plotting it against, what I'm very interested in, is how, if I'm at DC versus if I start changing the ones and zeros, I have frequency content there. I'm speeding things up, going faster and faster. And what I notice is if I make my channel very long, it has more loss. So this is looking at sweeping, going from 100 millimeter long channel length to 25 millimeters on this printed circuit board material that I'm going through. I can change that little dielectric absorption. And basically you can kind of step through with simulation tools and look at the effect of what's going to degrade or cause problems with your channel. So loss is one of them. It causes, at different, what do I say, at low frequencies you're going to have a different volume or magnitude of the signal than at higher frequencies. So what do we do with, how do we look at how well that signal transmits through a channel? So we're looking at bits of information, and we're going from, say, a 0 to a 1. So one of the things we can look at is how that edge goes through the channel. The next thing we can do is we can say, well, how does a single bit go through that channel? And we can see here, we can see the blue is when we put it, the transmitter is sending a single bit, but the receiver, we notice because of that loss in the channel, we've got some amplitude has decreased. Not all of the signal is getting through. That microwave, or was it like, just like your microwave, some of that energy is actually going into heating up the material rather than getting through. And then you can see things with simulations. I can do 10 gigabits per second. This bit is, I can do 10 billion of those per second. If I speed up my data rate, so I have 40 billion per second, my bit size gets smaller, and you can see my amplitude gets a lot less. So you're noticing now at higher data rates, my signal strength is less. And then I can put a whole, what we call a pseudo-random bit stream, or a random, it can be a whole bunch of zeros and a whole bunch of ones. And if you look at this graph, I'm putting a random bit stream in there to see what happens to it. All these different ones and zeros and different combinations. If you look at this graph, if I tried to plot, even 1 million bits, my graph paper would stretch beyond campus, probably go to San Francisco. How many people have tried to look at a plot with 1 million little transitions on it. Most of the time, if you drop all those transitions into a plot, it'll turn the whole thing blue. They'll all be on top of each other. It's not any use. So in the signal integrity world, they came up with a really neat trick. They said, what happens if I take all of these transitions, okay? So I have my rising edges here. I have my falling edges here. There's a rising edge, falling edge. And what I end up doing is I say, I'm really interested in seeing how all those transitions happen. And so what I'm going to do is I'm going to take all my rising edges. There's one that goes from a 0 to a 1. And I'm going to take all my falling edges from a 1 to a 0. And some of them are actually just, they go down. They're a single 0 bit, and they come back up. Some of them are a single 1 bit, and they come back down. And if you just start overlaying all of these on top of each other, you end up with what they call an eye diagram. And nothing really unique about calling an eye diagram. It actually looks like an eye. And all that they've done here is taken all these rising and falling edges, and every time you have a rising edge, you overlay them, and every time you have a falling edge, you overlay it, and then some of the bits are coming back up, so you end up with this eye pattern. And it's actually a really slick way of looking at thousands or millions of transitions all on top of each other. And instruments will run, they'll let them run for hours or even days, capturing, measuring to see whether any of these bits land in the middle of the eye where it would have trouble deciding whether it's a 1 or a 0. So if you look at it, when you make a transition from a 0 to a 1 or a 1 to a 0, what's the most important thing when you're trying to communicate? You want to know, is that signal, did you say yes or did you say no? Okay, you want to be able to receive that very clearly. And so here you can see that if I'm in the middle of this eye after I've made my transition and I say, okay, receiver, now you can listen and tell me what signal you see. This is clearly a 1. This is clearly a 0 down here. There's lots of how would I say, clarity between the 1s and 0s. But as you start, here you can see off on the right, if you have a lot of loss in your channel, you can see that loss ends up causing some degradation in how this eye opening is. And now there's a little bit less, separation between your 1 and your 0. And if the loss gets great enough, eventually the eye closes. So some of the bits that are going transitioning really fast between the 1s and 0s don't have enough time to actually get to a 1 level before they're trying to go back down to a 0, and then there's no separation. So that's basically, this is really a quick chart on understanding how we look at these digital patterns that are going through the physical layer. And one of the key ways of doing that is with an eye diagram, and we can measure the width of the opening, the height of the opening, and see how much separation we have between the 1s and 0s and how easy it is to differentiate or measure those. So now we're going to get into a little bit more fun physics, and it's a little bit harder to explain, but we're going to give it a try. And before we do, we're going to talk about 3 basic building blocks, and this is one of the things that I find very interesting about signal integrity. How many people have heard of resistors, capacitors, and inductors? Okay. I hate to say it, but that's about all I get to deal with signal integrity. And I keep thinking they're so simple. This should be an easy field of engineering. But what we'll find is it's actually, there's a lot to these 3 little components. Your resistor, obviously, it's at steady state. You've got your current equals the voltage divided by the resistance. The capacitor actually is a very unique device. It is for charge storage. The current flow equals capacitance times the rate of voltage change. So basically, a capacitor kind of looks like a short. And when you start flowing current into it, the current is very high at first because the voltage is 0 and you're charging it up. And as the capacitor charges up or your battery charges up, eventually the current slows down and you end up at a static voltage. But the relationship there is that the current is determined by the capacitance and how fast the voltage is changing on it. And then we have and this is more your static, or what I say, your electric fields between the two plates here for charge storage. The inductor is actually kind of neat. The inductor has more to do with the magnetic fields, and its voltage equals inductance times the rate of current change. And what we'll find here, voltage equals inductance times how fast the current is changing. And what you find is you flow current through the wire, it's setting up these magnetic fields, and if you try to stop the current real fast, you'll get a voltage spike, because any fast change in the current ends up with a spike in voltage. And the same thing here, if you have a fast change in the voltage, you'll get a large current flowing. But it's interesting that if you look at these things in terms of the concept that, again, we can't time travel. So you can look at a circuit and you say, okay, I can use what we call lump theory, or we can use these equations to solve what a circuit will do. But when you look at a transmitter to a receiver and that long path in there, what you find out is that you can't see, the transmitter can't see what's at the other end, okay? It doesn't know what's at the other end of that line. And so all you can do, all that the transmitter can see, is just a little ways in front of him. And there's a famous engineer, Oliver Heaviside, and he did a really neat trick. He took the transmission line, and instead of trying to solve this electrical problem by looking at the full path between the transmitter and receiver, he said, well, what happens if I look at that cable or that wire as just a short little piece of it? And so he looked at just a short section, and basically that wire has some resistance, there's some inductance, and then there's some capacitance to ground. Because if you have a voltage, it's going to the current's going to flow, and you're going to be in relation to a return path. So he came up with a simple circuit, and if you take that little piece of the cable, and you can use calculus to basically integrate all those little pieces together to make one giant long cable or path. And then he put a sinusoidal, or not a static DC signal, and he put a changing signal in. And he came up with these equations here. And what's really, the math you can go through. I'm sure a lot of you in engineering classes, you'll sit down in a quiet time, and it's very beautiful and elegant to go through the Telegrapher equations. But usually when it's quiet and you don't have someone bothering you. But the neat thing that came out of it is the fact that there's a characteristic impedance that is based upon this cable that sets up how much current is going to flow. And that characteristic impedance is based on the inductance and the capacitance. And then there's this funny little equation down here that's called a reflection coefficient. And what it says is if this impedance along the line changes, if the impedance at the source is different than the impedance at the load, because the transmitter doesn't know what the receiver impedance is. If they're not the same, you get a reflection. Okay, again, lots of math, hard to understand. What are we talking about? Eric Bogatin kind of came up with a really neat way of looking at it. He said, a lot of those Telegrapher equations and Maxwell's equations and stuff, it gets a little complicated. What if we just think about, we've got a wire, okay, we're going to put a voltage on that wire, and we're going to see what happens as that voltage starts to ramp up. Okay, we've got that little ramping edge. We're going to start to ramp that voltage up. As we start to put voltage on the wire, there's got to be ground somewhere. You kind of have to have this return path. A circuit doesn't work without the current flowing. And what you have is this current basically, you're charging up the capacitance of the line. And that's how the voltage ramps up. There's a little bit of current flow to charge up that capacitance. And then you step forward and you charge up the next little capacitor. And you step forward and you charge up the next little capacitor. And so that's essentially what's happening as you're walking along with this voltage and it's traveling down this wire. And from that derivation, he can basically come up with the impedance is 1 over the velocity, how fast you're walking, times the capacitance. Again, it's one way of looking at it. I actually like to have another way. And this one even gets simpler. we're talking about reflections, okay? So how do these really happen? I'm charging up the line. I can only see what's in front of me. And so when I first put that voltage on there, it starts to flow a little bit of current based upon this characteristic impedance. And it's going to start flowing that voltage with that current is starting to flow down the wire. And if it gets to the other end and it's not the same, you're going to get a reflection. Well, what does that mean? If I put an open there, it's a lot easier to understand. If I turn my watering hose on in the garden, okay, and the water starts racing down the water hose. If it's in this case, how do I want to say? If it's in terms of electrical things, when I say it's open, it's blocked at the end. Okay, I'm not going to let it's not connect. Let's see, maybe that's not the right. So essentially, what happens is I'm flowing my current down here. And at the open end here, there's no place for it to go. It's not connected. So it'd be like the hose on my watering hose being blocked. But I have all this water going down there. I have all this current flowing. It can't go anywhere, okay? It just got to the receiver, and the receiver says, I'm not connected to anything. You got to go back. So all that current that went racing down here now has to turn around and come back, and that's where you get this voltage increase. And it's a reflection. So basically, all the current, the transmitter started sending current down here with a certain voltage pressure, and suddenly it gets to the end and there's no place to go, and that current has to come back. Very simple reflection to understand. You started putting something down the line, you get to the end, and there's no place to go, it comes back. How many people have been on the freeway when there's a traffic accident? You got this nice flow of cars going down the road. Someone has an accident. Nobody's going through anymore. Have you ever kind of watched how that ripple starts reflecting back? And it goes back far enough to tell everybody back there, hey, slow down, we can't keep flowing all those cars. So this is called impedance matching, because you want the flow to continue through there. And that's when I think of driving on the freeway and I watch all these cars, I constantly think of impedance matching. What flow do I want to go at so I don't actually have to put the brakes on and cause a reflection? If you have a short, this is the other example. If you start flowing stuff, the current down this wire and it gets to the end, you have a certain impedance that's setting up a certain current. But if that impedance goes away, if it's a direct short to ground, then you're basically saying it's 0 volts. If you short something or have no resistance, then it has to go to 0 volts. And so here your voltage is traveling down the wire, and suddenly all that current just goes away, or drops to ground without any, brings the voltage down to 0. And so you essentially get this reflection of a negative voltage step going back. So if the key thing here is if you don't have the same impedance, whether it's an open or a short, you're going to get a reflection coming back. So the whole trick is to try to have the same impedance at the transmitter as you have at the receiver, and then you won't get any of these reflections. So that everybody's traveling at the same speed, same current, and then when you get to the end, you have that same resistance and the same current flows. So basically that's a lot of what the signal integrity engineer does, is he spends a lot of time trying to figure out how to keep the impedance the same in that channel. Now this is where we look at the size of things. Now we talked about that at faster and faster data rates, our edge is, the rising edge is getting faster and faster. And what we can look at is if I take that transmission line, so I have my cable, and I've put an impedance mismatch, or a change in impedance in the middle of the cable. So, if I'm going down that cable at a certain speed, or I'm traveling down the freeway, suddenly it goes from, say, 5 lanes to 2 lanes. Well, what happens? You get a reflection as everybody kind of slows down, and a wave of everybody has to kind of slow down their speed. And that's essentially what I've done here, is I put an impedance reflection in the middle. And you can use simulations to see what happens if it's long compared to that step edge length. Then I get a big reflection. If it's very short compared to the rising or falling edge, there's less of a reflection. But the point of this that I want to make is that the length of this discontinuity, if it is long compared to that rising edge, I can get a fairly large reflection. And if I look at the data rates, megabits was where we were back in the 70s, 70s and 80s. We are now at the 40 gigabit range. If we look back at what was happening, 1 megabit was about 3 meters or 10 feet long. Okay, that rising edge at that low speed was very slow edge compared to our printed circuit boards, compared to the cables, you know, your USB cable and these different things. So you really didn't care about the impedance of those that channel as much. But as you start going up in data rate, you'll find that that rising edge is getting taking up, how I want to say it, is the rising edge is getting faster, and it's actually taking less distance to transition. And so we go from something that was 3 meters long to go from a 1 to a 0 to say right now we're looking at 40 gigabits, being able to transition from a 1 to a 0 in amount of mils, okay, thousandths of an inch. And what that means is, and one of my little projects a long time ago, actually when I was with Don Extra's group, were little connectors to transition an electrical signal into a printed circuit board. And if you want to look at the details on here, you can see the level of effort trying to match the impedance as you go from a circular cable into a planar printed circuit board. And what you find is a lot of what signal integrity engineering is. In the past, we might have worried about the impedance of the cable being, say, 50 ohms matched with our transmitter and receiver. Now, as we are at 40 gigabits, we're actually worried about the machining tolerances of connectors, the actual etching of the traces on the printed circuit board and the layers and how the different mechanical features are affecting our electrical performance. So it's a lot of it is about size and what becomes important as you start to speed things up. Again, this is where simulation can actually add a lot of advantage, and the next slide is a little more exciting, but the key thing here is with simulation, I don't have to crunch through all of the equations to look at how these reflections, if I can look at one impedance mismatch, that's pretty easy to understand, but if I start stacking a whole bunch of impedance changes in a channel, I'm going to get multiple reflections, and then the mathematics starts to get a lot more complicated. So this is where we put, here's a transmission line, and I have a short stub hanging off of it. Here's another transmission line, and the wire got wider. Two different types of impedance discontinuities. I can put that into a simulation tool. And now I can look at, we had our plot earlier. I can see if I put a signal in at a DC frequency, then all the signal comes out. But as I increase the frequency, I notice there's certain places where the signal doesn't come through. So this stub is causing some very interesting reflections. As the signal goes down this stub and then reflects back, because the current goes down here and it can't go anywhere, it comes back. And there's multiple bits in this path. They start interacting and overlapping. And so at certain frequencies, those interactions can actually cancel. And you can see the eye opening is looking rather strange, overlaying those rising and falling edges. And essentially, if that eye closes, we can't tell the difference between ones and zeros. So just kind of fun with a simulation tool, I can start to see how long of a stub length is going to affect my performance. And here, if I make my stub, 10 millimeters is very long, and I'm getting lots of reflections that are canceling out. If I make that stub very short, you can see that all the signal is going through now, which is out here. So again, simulation tools quickly tell me what stub length maybe is important for the data rate that I want to transmit at. Again, we have the series impedance discontinuity. Just a different type. This one causes more of a smaller variation, but again, if I make it short compared to my rising edge, then all the signal goes through. So again, just kind of the key thing here that I wanted to kind of get across is that reflections can get kind of complicated, and so the simulation tools become very powerful, but understanding the basic concept of why reflections happen is the most important thing so that you can understand what simulations need to be done. Okay, a lot about signal integrity, getting communication from the transmitter to the receiver. What do you think happens if there's no power to your transmitter and receiver? Can it talk? No, okay. So there's another part of the world that is also becoming very important, and we already gave the signal integrity engineers a name, and so suddenly we start having power integrity engineers pop up. Well, what does a power integrity engineer do? And again, it's actually pretty cool. We still can't time travel, and that's what it basically comes down to again. You've got a supply, and here I have kind of a fun water tower. You've got your supply of water or your current and then you have your consumer, and in our case, your your transmitter and receiver over here need power to talk, okay? When they're talking at full strength, they need a lot of water. When they're quiet and no information transmitting, they don't need any power. So the supply over here is not right next to the consumer. There's some distance there. It takes time for that supply to respond to demand. So if this supply over here turns on its flow of water, and the consumer says, we're parched, we got all sorts of people talking and yelling at the same time, we need lots of power, lots of current, lots of water. So you ramp up to a maximum flow rate, and then those transmitter and receiver said, oh, we're done. There is a whole lot of water or current flowing down that pipe or that fire hose of delivery system there. It's got to go somewhere. It can't just disappear. And again, it's that same concept we had in the channel. You get sort of a reflection that can kind of happen. That current has to go somewhere. And so what you find is that power integrity basically boils down to the ability to place capacitors. Remember how we talked about a capacitor stores current? So what you can do is you can place capacitors close to your transmitter and receiver, and any extra current, once the transmitters and receivers say we're done talking, the extra current can go into charging up the capacitors right next to the device and give the power supply time to turn off. The same thing goes the other way. If the device suddenly turns on, the power supply can't turn on that fast, but these little capacitors close by can start dumping charge into the transmitter and receiver. So it's a very simple explanation, but if people are asking you about, if you ever thought about power electronics and some of the challenges there, a lot of what it comes down to is the fact that the power is not next to the consumer, okay? And there's a lot of challenges in how you store energy along that path and make sure you've got enough local charge storage to absorb or deliver current while your power supply slowly catches up. So again, really kind of the same problem as the signal integrity engineers working with. And I think this brings us to sort of the end of my talk. And I was looking at this, and it's one of those things with engineering. You'll find that when you're working on projects and things just don't seem to go fast enough, but when you look back, it's amazing how fast the technology changes. And here's one that 2 years ago in March 2012 was the last hard copy of the Encyclopedia Britannica. There were 32 volumes, it weighed 129 pounds, and it took about 8 billion bits to store the text data for this Encyclopedia Britannica. The fastest transmitter and receivers that we have today are transmitting about 10 billion bits per second. So in 1 second, you could pretty much transmit about the same number of bits or more than the whole Encyclopedia Britannica. And it's just interesting to kind of look at it that way. Another one that's kind of wild, I sometimes think about is it would take like 2.5, or was it like 2 lifetimes. If you started counting bits at about 1 bit per second, 1, 2, 3, 4, 5, etc., you'd be around. You'd never get to the 10 billion bits that we're transmitting in 1 second today. And then if you look at how the electronic era is going, Wikipedia is already 55 times bigger than the Encyclopedia Britannica. The amount of information that's racing around in these server farms, these clouds, is just incredible these days. So something to think about as you go into engineering and start applying your skills. My advice is to have fun with it and take advantage of what comes in front of you. Most things that you'll deal with have some sort of engineering aspect, and a lot of exciting technology out there yet to be invented. So good luck, and thank you for attending my talk today.
Can I ask you a question? How, if we bring in the noise aspect to the integrity, can you add something to that?
Right, I didn't talk too much about it. Basically, let's see, there's different types of noise. And I think the simplest one is we just talked about power integrity and what happens if, you want your signal to go from a 0 to a 1, say, but if all of the transmitters suddenly go from a 0 to a 1 and they're asking for more power and there's not enough current, then what you're going to find is instead of coming up to a 1, it's going to maybe do some funny ringing or noise in there because it's literally not getting enough current from the power supply. And how that power supply current is getting to the transmitter receiver can affect noise there. There's also the problem of if you have what we call a trace, and you have another trace nearby. And this is kind of an interest. I didn't go into a lot of detail here. When you have, we talked about how when you're walking down that cable and you're charging it up, okay, there's a return path. And if you think about it, the electrical, when I apply a voltage, it's going to look for that return path. It's going to look for where's some metal, where's ground, where's a return path for the current to flow. And what it's basically going to do is it's going to look for whatever the closest conductor is. It doesn't understand ground. It doesn't understand what metal it's supposed to really be flowing through. It just says, what's the nearest conductor that I can set up these electric field, this capacitance to? And we call that the return path. So even though if, I don't know, actually I should probably draw this a different way. Let me go with this, we'll draw a cross section. So if I have a trace on top of a printed circuit board here. And what I really want is the electric field to be set up here so that my return current, my capacitance, comes from this trace, this copper wire here, down to a big copper plane return path. But if I put another trace right next to it, and it gets too close, like I said, it doesn't know that this is my ground return. Just because I put it on the schematic that this is ground, the signal doesn't care. It says this copper is closer. And so you'll get essentially electric fields coupling over here, and some of the energy will transfer over to the other trace. So as you bring wires together, they'll start coupling, and some of the fields will start creating return currents on this other cable, and then that can cause noise. So that's a coupling type of interaction.
Is the ground the number one problem that people run into on these very high-speed boards?
So the fact you say ground is the one of the biggest problems, because when you start doing electrical circuit design, they give you a schematic, and schematics have these wonderful symbols that say ground. They draw little arrows, sometimes they're like that. And that basically, you on your schematic, you're showing where you want all the current to flow, and then you put this funny little symbol there and say everything magically returns back through there to get to this power supply. Has anybody hooked up a battery where you only connect one side of it? Does the light bulb turn on? No. You have to have a loop. You have to have a return path for the current to flow around that loop. And the same thing with a schematic. When you're working with electrical circuits, you can draw that path where the voltage or your signal's traveling, but he also has to come back through a path. And what happens with high speed, like I was talking about, it's going to look for wherever the closest metal is. And even though I have a big area that I've said that's my ground return path, if there's metal closer to the signal, it's going to jump over there and go different directions. So I think the biggest problem we have with high speed, high frequency design, high speed circuit design is that because the schematic doesn't define it, when you get to the layout, when you actually start laying out the circuit, people forget where that return path is. They're not thinking, okay, where's the closest return path for my signal? What metals, how the metals are close to each other and interacting. So, is that?
Yeah, that's what I thought.
Actually, you know more than I do, but.
If I were going to design the highest speed board possible,
Mm-hmm.
what's the state of the art now in terms of materials and line spaces and that type of thing?
So one of the interesting things is they have what they call speed board that basically lowers the dielectric constant so the velocity is faster on it. Sounds better, can be better, but what ends up happening a lot of what's really killing us with high speeds digital systems and even RF microwave a lot of times is not so much necessarily the loss, how do I want to say, the actual loss of the material as much as the repeatability or the uniformity. I talked about how as you get to these very fast edge rates that you literally need to match impedance down to like the matter of mils, the machining tolerances. Well, we're starting to get down to the point where we can actually see the fiberglass weave in the printed circuit boards. We can see the variations in thickness when they go to create these layered materials. So a lot of what the new materials are doing is figuring out how to reduce losses, but also have a very uniform material. They're looking at composite materials to get the right characteristics, but very fine, I think like nano-sized particles, and trying to get that material very uniform compared to the side, the rising and falling edges. So I think that. But yeah, I think that's another very rapidly growing area of engineering right now is all the printed circuit board
So there really
materials.
is work going on in that area.
It's very competitive. They'll find a material that works great for high speed, and then they'll discover that mechanically it has some problems because maybe it absorbs too much moisture in certain conditions, or the Z expansion is too much and it actually cracks the via connections that are going from between the different layers. So a lot of challenges with printed circuit board fabrication.
I have another question. This the diagram that we had before this, you had a lot of the capacitors being added so that to make the power transmission most efficient. In fact, basically counteract with the inductance of the lines.
Mm-hmm.
Now, when it comes to the high-speed bit transmission, you really want to reduce all of these capacitances so that it would not.
It actually comes down to, it's still impedance matching.
Yeah.
And the difference is, on the transmission line, my impedance is 50 ohms. And so, again, if I have perfect 50 ohm match everywhere, my signal just goes down, okay? What typically happens with high-speed transmission lines, though, somebody forgets to put the ground return close by. That causes an inductance. And so, typically, that's the first sort of problems you run into is there's inductance because the impedance is set by the relation between the wire and the return path. And if that return path going through a connector or transitioning, the signal transitions, we talked about, the schematic, there's this funny symbol. Well, you route your signal and it goes where you want it to, but nobody paid attention to how the return path's trying to follow it. So the return path is left to find its own way, and that's inductive. So it basically, it goes back to inductive, okay. But if you look at power delivery, the impedance is milliohms. Okay, we're talking 50 milliohms. And so down at that impedance level, you're much more sensitive to the inductance in the path. So if you look at that LC combination that gives you the 50 ohms versus 50 milliohms. But again, it's a lot of it's the impedance matching again.
I think they pizza is there, right?
Yep. So pizza time.
Now, I would like to. You have a
I have one other question. In the transatlantic cable of 1858, the so-called quote engineering quote, what happened to it?
Well, they brought in a physicist to actually look at the physics of what was going on, but I believe it was a different company that got funding the next time around.
Well, as you know, in fact, we invited Heidi for the Women History Month, and I'm glad that she accepted our invitation. And I really enjoyed her talk. It was quite interesting and also insightful. So let's just